Hi, this video will go through the major concepts, contributions, and results that were made in the paper Make an Audio Text-to-Audio Generation with Prompt-Enhanced Diffusion Models that was published in ICML in 2023. While text-to-image and text-to-video generation have achieved major milestones, the application of such methods to audio still lags behind. And why is that? Well, there are two key challenges: a lack of large-scale datasets with high-quality text-audio pairs, and the difficulty in modeling long continuous audio data. The solution Make an Audio propose is using prompt-enhanced diffusion models with two major innovations: pseudo-prompt enhancement, which helps mitigate data scarcity, and spectrogram autoencoders predicting self-supervised audio representations instead of raw waveforms. Pseudo-prompt enhancement is Make an Audio's method of combating the data scarcity problem. It comprises of two parts: expert distillation, which uses pre-trained models to do auto-captioning and audio text retrieval to gather more data, and dynamic reprogramming, which is cutting up audio samples and mixing them together to get more complex sounds. This both helps against overfitting and creates more complex sounds in the training set. Now, after using pseudo-prompt enhancement, we've gained a diverse dataset of text and audio pairs, so we can now train our model. The model composes of an encoder network, which takes the MEL spectrograms and projects them into a latent space. In this latent space, a diffusion process will gradually denoise the image. After this is projected back into a MEL spectrogram, where a discriminator network will apply the GAN loss to it. After all this, a vocoder will convert the MEL spectrogram into a normal waveform. To align the modalities of text and audio in the latent space, contrastive pre-training is used. So the famous model CLIP from OpenAI have shown to be very effective in the language image domain. And as we're representing our audio as MEL spectrograms, we can use much of the same architecture, but a new pre-trained model called CLAP is then used. And the quality of this pre-training is very important, as better alignment means better prompt faithfulness.
The authors demonstrate the ability to generate quality audio from any user-defined modality, highlighting the potential to connect the visual and audio worlds. For example, to create audio from images and video, frames are put through a clip encoder to create embedding vectors, which are then fed to Make an Audio to generate samples. Beyond visual to audio generation, this approach can be extended to other modalities as long as the corresponding inputs can be reasonably captured by an associated embedding vector. Looking at some of the results, here's a few samples generated from the model. For instance, a bird chirping, a car engine, and a baby crying. From the quantitative findings, we see that Make an Audio performs well on almost all the benchmark tests, demonstrating high fidelity generation with realistic output. Looking at Table 1, we observe that Make an Audio has higher quality than a comparable model diff sound, with a minimized FID score of 4.61 and a KL divergence score of 2.79. Make an Audio also outperforms diff sound in terms of subjective quality, with collected mean opinion scores regarding quality and faithfulness just below the reference values. Make an Audio also performs well for audio inpainting and achieves fairly high subjective quality for visual to audio generation. In terms of the qualitative results, the model seems to generate audio with the trade-off of realism and faithfulness, depending on the classifier-free guidance values. In general, the closer the sample is to the prompt, the less realistic it will sound. We can also observe that Make an Audio performs well at audio inpainting, even for a variety of masks. In terms of some of the key takeaways, as we just discussed, Make an Audio outperforms current state-of-the-art, tested on both objective and subjective benchmarks. This work serves as the basis for future audio synthesis work, and it's already been utilized in other projects, such as Audio GPT, which combines many different audio synthesis models with the powerful language processing of ChatGPT. In the past, it's been difficult to train high-fidelity audio synthesis models due to a lack of large-scale datasets. The pseudo-prompt enhancement with the distilled and reprogram approach alleviates this data scarcity problem, creating concept compositions with language-free audio to build new training examples. Additionally, By predicting self-supervised audio representations instead of waveforms, Make-In Audio guarantees efficient compression with high-level semantic understanding. Finally, combining these approaches with CLAP, or contrastive language audio pre-training, the model demonstrates a deep understanding of language with high-fidelity generation. If you'd like to learn more, we've provided the links for the associated paper and GitHub project. Thank you.